All right. Oops, forgot to delete that today. All right, so the plan for today is just to go through, we'll start going through chapter 12 on the 3D coordinate system and vectors. Note that this week is the Unit 3 exam week. I'll probably send out an announcement this afternoon as well, just in case anybody didn't make it to class today and maybe forgot that this was exam week, but Unit 3 exam is posted, the sample exam is posted. It'll be taken on WebAssign with Examity, similar setup as Unit 1 and 2 exams. The final, just remember, it will be available Friday 5/3, so this coming Friday. It's hard to believe we're already there, but Friday 5/3 through Friday 5/10. Same setup, WebAssign with Examity. The sample exam is available now, and you may use a formula sheet. So you can use one kind of standard, roughly printer paper size sheet of paper, front and back, with any formulas, notes, anything like that that you might want on it. You can also use, if you want to print off that workflow series workflow testing sheet or anything like that, you can use basically whatever you want on the front and back of one piece of paper. And strongly caution you to complete the final exam by Wednesday, or plan to complete the final exam by Wednesday the 8th at the latest. That way, if you log in on Monday, Tuesday, Wednesday, something like that, and go to complete the final, and something happens, if Examity isn't working quite right, or something happens with your power or internet or whatever it may be, that gives you some buffer to work out a solution. If you wait until Friday, or even worse, like Friday night, to complete the exam, you're taking a huge risk with your grade. There are no due date extensions for the final exam. I need to get all of my exams and everything for my 6 sections graded, the grades completed, everything turned around and uploaded as quickly as possible, because students are looking at summer session classes and so on, so those need to be in pretty quickly. Again, the goal today is to start chapter 12. We do have a regular class meeting Monday, a week from today. Final exam week officially goes through Tuesday. I guess that's Tuesday the 7th through the following Monday. But we do have one last class meeting that kind of Monday right before final exam week. So we'll wrap up anything in chapter 12 that we need that day, and any just general course wrap up, any questions, anything like that. And then Wednesday the 8th is an optional review session. Again, I'll pretty much just treat it like office hours from 1 to 3 p.m. If you have any last questions or anything like that, you can feel free to log on. But don't feel obligated to come if you don't want to, especially if you've already taken the exam and you're in summer mode. You don't need to show up to that, but if you want to, if you have any questions, I'll be here. But I'm just making that available because we have to do something during that final exam time. So that'll just be an optional review session. Sorry, my allergies have been haywire the last week or so. Was doing good this morning, and then right at the end of stats class, right at around 11:45 or so, started getting worse. Anyway, so that is the plan coming up here. I know you guys are balancing a lot of things on your plate, so I try to, these last couple weeks, kind of remind you of what we've got going on in this class a little more regularly, just so you can kind of plan your last little bit of your semester. All right, are there any questions on anything before we get into the material? Okay, let me just bring up my notes here. There we go. Okay, so moving into chapter 12, the 3D coordinate system is what we'll start with. Calc 3 is really what we're kind of kind of leading into here, I mentioned before that, this topic used to be part of Calc 3, and some of the integration material that we cover at the end of Calc 1 used to be part of Calc 2. It was a little more sensibly, I suppose, divided between the three courses. But then, for engineering and some of the applied um, the applied sciences, they wanted us to start covering vector calc and Calc 3. So that pushed a bit of that pushed like chapter 12 into Calc 2, and that pushed a little bit of integration out of Calc 1. So the dividing lines are a little less sensible, at least at first glance, than they used to be. But that's why we're starting into this material in Calc 2. So this is going to seem like, like a maybe substantial deviation from what we've been doing for most of the course, and it kind of is. But Calc 3 really focuses on, for the most part, multivariable calculus, and in some sense, a lot of it is kind of revisiting a lot of the Calc 1 topics and some Calc 2 topics, but in more than one dimension. So that's why we're discussing the 3D coordinate system. And, if you've taken physics or physics or engineering courses like statics, things like that, vectors are probably somewhat familiar to you already, but you might not have seen that already. So we're just going to cover things from kind of first principles. So if we think in terms of a two-dimensional coordinate system, say X and Y, if I have a point here at position X comma Y, I can think that this means start at the origin, go along the x-axis, little x units, and then turn and go parallel to the y-axis, little y units, and that's what we mean by x comma y in this Cartesian or rectangular coordinate system. So what if I have a 3D coordinate system, also kind of a rectangular coordinate system? X, Y, Z. And if I have some point here, which kind of unfortunately, when you're trying to draw 3D in a 2D plane, it's, not really clear where this point is, but we'll make it a little clearer here in a second. So what if I say that this is point little x, little y, little z? What I mean by that is start at the origin, go little x distance along the x-axis, then turn and go parallel to the y-axis, little y distance, and then turn again and go parallel to the z-axis, little z distance. So this is our 2D plane. This is our 3D space. So I note that in my 2D plane, I have two spatial dimensions available, and I need I need two descriptive pieces, a first component and a second component, to say where I am in that plane. Or another way of looking at it is I have 2 degrees of freedom. I have two things that I can move around. I can move the horizontal position of my point, and I can move the vertical position of my point. And I need to, if I want to describe where a point is, I need to say what horizontal and what vertical position it is. Or perhaps, maybe in another context, I can describe the location of that point in a different way, something like, say, polar coordinates, but I would still need 2 components to describe where that point is. I have 2 degrees of freedom. I need to tell you 2 things to say where that point is. In a 3D system, I have 3 spatial dimensions. I have 3 degrees of freedom. I can move, say, left to right, forwards or backwards, and up or down. I need to give you 3 descriptive pieces of information to say where that point's located. If I impose a constraint, say for instance, like z equals 1 in 3D, then what does that kind of mean? Well, what this means is that the points in 3D space that satisfy the constraint z equals 1 all have to look like, well, little x can be, the first component can be kind of whatever it wants, the second can be whatever it wants, but the third has to always be 1. So I know that I've always got to be at height 1, but I can be anywhere front to back. I can be anywhere left to right as long as I'm at height 1. So this plane goes through x equals 0, y equals 0, z equals 1, and then extends out in the x and y directions forever. Or it's basically a copy of this 2D plane up here, kind of embedded in 3D. I have the three-dimensional space I'm working with, so I have 3 degrees of freedom. I have 1 constraint. And typically what happens is when you impose 1 constraint, you lose 1 degree of freedom. I have 2 degrees of freedom left over. If I'm operating under the constraint z equals 1, I can now kind of move freely, but only in these 2 dimensions, only in the x and y direction. I'm kind of stuck at z equals 1, right? It's a little bit similar to kind of how we're on the surface of the Earth and we exist in 3-dimensional space. We can move like relative to our positioning up, down, forwards, backwards, left, or right. But like within reason, we're pretty much constrained up and down to be on the surface of the Earth. I mean, unless we build a rocket ship or something like that, but we're pretty much constrained to be on the surface of the Earth. So if we have that constraint that we're on the surface of the Earth, I can really only move forwards and backwards or left and right. I can't really move up and down, at least not easily, right? Now, maybe I can jump or something, but I can't move very much up and down. So it's a little bit like that. I have kind of start with 3 dimensions that in theory I can move up, down, forward, backwards, left, right. But if I can impose a constraint, you got to stay on the surface of the Earth. Well, now you're down to 2 degrees of freedom, forwards and backwards or left and right. So we have a distance formula in 2D. The distance formula in 2D between 2 points, say x1, y1, and x2, y2 is just the sum of the squared differences between the variables under the square root. It's completely analogous in 3D. And it's not hard to show this. We can look at the distance between, say, these 2 points, and we see that that's by the Pythagorean theorem, right triangle. This green distance is going to be, say, root x minus, or x2 minus x1 squared plus y2 minus y1 squared. I'm just using this picture as kind of a rough diagram. We don't necessarily have to start at the origin, but. And then I would be interested in finding this distance from the point that I started at to the point I end at. I want to find the blue distance. That's what I wanted to find from the beginning. I find the green distance to begin with. And then the blue distance is the green distance squared plus, well, then I have my height, my z2 minus z1 squared, and that's under the square root, right? Or the green distance squared is just those 2 squares. So I just get rid of the square root, tack on the z's, put the square root back on, basically. right? Completely analogous to the 2D version because we're just applying good old Pythagorean theorem just twice here in succession. So what's the distance between these 2 points in 3D space? If I was going to draw a straight line going through 3 dimensions, well, the distance is just the square root of, it doesn't much matter what I pick to be 0.0 or 0.1, as long as I'm careful with my negative signs. So -1 minus a -4 is +4 squared. -1 minus a -1 is +1 squared. And -1 minus 3 squared, all under the radical. -1 plus 4 is +3 squared is 9. This bit gives me 0. My y position didn't change, so I went 0 distance there. And my z position, how did it change? It changed by 4 units, so this is -4 squared is 16. Square root of 25 is 5. My x position changed by 3 units, y by 0, and z by 4. So this is just a 3, 4, 5 triangle. Pretty straightforward, I think, for the distance formula. Basically the same as 2D. Let's think about these next couple examples. These are kind of related to this degrees of freedom and constraints ideas up here. So here I have an equation, y equals x. Let's consider what it represents in a 2D space versus a 3D space. So in a 2D space, x and y, I just kind of know from experience that y equals x is this line. Is that, sensible at a deeper level? Well, we have a 2D space, so we have 2 degrees of freedom. We have imposed the constraint that y equals x. In other words, the second component, when you choose a number for the first component, the second component has to be that same number. One constraint. We have 1 degree of freedom left over. We get, well, what's 1 degree of freedom if I can only move left or right? If I can only move in one direction or its opposite direction, that's a line. Sometimes it could be a curve. Maybe it's a curved line, but you still, if you're standing on this curve, you can only move this way or the opposite way. You can't move in some orthogonal way. And 1 degree of freedom is a line or a curve. So that makes sense. In 3D, what does this represent? Well, again, we start with 3 degrees of freedom. Degrees of freedom. We have 1 constraint. Looks like we're left with 2 degrees of freedom left over. We would expect a 2-dimensional structure, something like a plane or maybe more generally a surface of some sort. So what do my points look like? I can choose x any way that I want. But once I choose x, y is fixed. Y also has to be x. And then my third component can be whatever I want. So I have 2 degrees of freedom. And then once I pick x, the second component is fixed. So if I have y equals x, in the case when z equals 0, that's just this line. This line in the xy plane. This is when z equals 0. But in the case that say z equals 1, I just get a copy of that line, but 1 unit higher. Or when z equals 2, another copy, just another unit higher. Or when z equals -1, another copy, just one unit below the original one. I just get this vertical plane that's kind of coming out of the screen at 45 degrees between x and y, and that's going straight up and down. So z can be whatever I want it to be. That's what sets the height where I'm at on this plane. And then once I pick x or y, the other one of those is determined because I have to stay on the plane. So I do see that I get a two-dimensional object left over. That's a plane. So a similar looking equation can represent something different in 2D space versus 3D space. The context does matter. What about this example? The equation x squared plus y squared equals r squared. What does that represent in a 2D space versus a 3D space? So just like above, we start in the 2D space with 2 degrees of freedom. We have one constraint. We have some constraint on the relationship between x and y. We should end up with 1 degree of freedom left, something that's a line, or at least line-like, a curve, something like that, something one-dimensional is what we'd expect. X squared plus y squared equals r squared. Well, that looks like a circle with radius r. Now, again, is this one-dimensional? I mean, at a glance, you might say that this is a two-dimensional object because I kind of need 2 dimensions to write it in some sense, but imagine you were standing on this circle and you're not allowed to step off the circle. You really only have one choice. You can go this way or the opposite way. You can't go this way. You can't go that way. So this is one-dimensional. If you're standing at a point, you can only go left or right. You can't go forward and backwards. That would take you off of the circle. So this curve is a one-dimensional object. This is what we would expect, starting with 2 degrees of freedom, imposing one constraint, being left with 1 degree of freedom. We get a one-dimensional object. We can choose where we're at on the circle, how far to go left or right from some starting point. But when I choose how far to go left or right from some starting point in conjunction with this constraint, that uniquely determines my position. What about in 3D space, though? Again, we would expect something plane-like, where if we're constrained to be standing on that object, we could go, say, forwards or backwards, or left or right, but maybe not up or down, something along those lines. What would this look like in 3D space? Well, it's often super helpful to, just like I did up here, start by imposing a condition to just make something a little easier to draw. If I impose z equals 0, what would, oops, wrong direction. I have one dimension of directions in my pens up there. I managed to choose the wrong direction. But if I impose z equals 0, in addition to x squared plus y squared equals r squared, what would that look like? That would look like a circle in the xy plane. That would look like something like this. I'm going to try to make it look like a circle, even though it's in a funny perspective. So because we're viewing it from an angle, it would maybe look a little more like an ellipse. I don't think that's a super great drawing, but that's, I think, good enough for our purposes. So sometimes if I have a more complicated relationship, I have 3 degrees of freedom of starting with. One constraint, I expect to get 2 degrees of freedom left over, but I can impose another constraint to get me down to something that's a line or a curve that I'm a little more familiar with drawing. And then I can ask what happens as I vary that constraint that I artificially imposed. What if z was 1 or 2 instead, or -1 or -2? Well, I note that if I change z a bit, that actually doesn't change this constraint at all. If z was 1, I would get just another copy of this circle, but just 1 unit higher. Or if z was -2, I'd get another copy of this circle, just 2 units lower. Maybe this is z equals 1. Maybe this is what I would get with z equals -2. Or really, I get a cylinder or a cylindrical surface, like a pot can with the top and bottom cut off of it. I started with 3 degrees of freedom. I imposed 1 constraint. I should end up with 2 degrees of freedom. If I imagine myself kind of like a little ant or something, kind of standing on the surface of a pot can, well, I can go like, in some sense, forwards or backwards, like around the radius of the can, or I can go like up or down, like along um, the z axis of the can. But I can't go this way or that way. I can't like jump off of the can or go inside of the can. I'm constrained to be on the surface. I can't go from this perspective for this person, what we're seeing, the left or right dimension. But my person can go up or down along z, or they can kind of go around the circular bit of the can. So this is like a plane. It's just a plane that's kind of wrapped around on itself. So it's kind of planar in nature. It's a surface. It has 2 degrees of freedom to it. Let's look at a related idea. What's the equation of a sphere in 3D space of radius r centered at h, k, and l? And if we wanted to be careful here, a sphere is really a surface, and a ball is the enclosed volume. So a sphere is a surface. Quite often, we just colloquially use the word sphere to mean a ball. So if I had something that was like a golf ball, like a filled-in spherical thing, quite often we would just call that a sphere. But being specific, in math, when we say a sphere, we mean the surface. And when we say a ball, we mean the kind of surface plus the filled-in volume on the inside. So what's the equation of a sphere in 3D space of radius r centered at a center HKL? So I have x, y, and z. I have some center h, comma, k, comma, l. And I have some radius r. And I have a sphere. And when I say a sphere, what do I mean? I mean the surface that is in every direction radius r away from the center. So that's what we mean by a sphere. It's the set of points that are the radius r away from the center HKL. I see this is going to be a surface because I start with 3 degrees of freedom. I start with 3 constraints, and I add 1 constraint that I want to only consider the points that are a specific radius away from a specific point. Well, what does that mean? That means if I have a point on the surface of the sphere, say x, comma, y, comma, z, the radius has to be r, or that means the distance from h comma k comma l to the point x comma y comma z, a point on the sphere, has to be constant. It has to be r. But we know what our 3D distance formula is. It's basically just the same as the 2D distance formula, right? Just with an extra little bit tacked on. So what's the distance from HKL to XYZ? That's square root of x minus h squared plus y minus k squared plus z minus l squared. That's what the distance between those 2 points is. And imposing that that has to be equal to r. This is my constraint. I start with 3 degrees of freedom. I impose one constraint. I get a 2-dimensional surface, right? If I'm standing on this surface, I can move kind of in this direction or like in this direction, but I can't move in that direction. I can't move like closer to the middle of the sphere or farther away from the middle of the sphere, or I would leave that surface. I would no longer satisfy this constraint. Or the way we'd often write this, we would often write it this way, right? The 3D analog of this 2D circle. Note that it doesn't really make sense to ask, what does x minus h squared plus y minus k squared plus z minus l squared equals r squared look like in 2D? Because we really fundamentally need 3 dimensions to describe this. We can kind of, in some sense, like underdetermine something in 3 dimensions. We can give a little less information. You know, we don't see any z's explicitly in here, but that's okay. That just means that the contribution for z is just going to be to basically create a whole bunch of copies of the same 2-dimensional structure. But if we have a fundamentally 3-dimensional structure like this, well, we're not going to be able to say, what does that look like in 2 dimensions? There's just a little too much information here to say what this would, you know, this similar equation would look like in 2 dimensions. We could maybe ask things like, what would a projection look like? Like if I imagined a light coming down from above, what would the shadow look like in the XY plane? You know, that's something that would be an important question to ask in Calc 3, or an important question to answer in Calc 3. We could ask questions like that, and those would be very useful questions to ask in the next course. But at this point, you know, just for this, we really need 3D. It's fundamentally 3D. But for something like these up here, we've got to know the context. Are we working in 2 dimensions or 3 dimensions? Any questions on anything so far? Okay. So that was 12.1, just kind of the basic introduction. Moving on to 12.2, vectors. So definition of vector is a quantity with both magnitude and direction. So some examples are velocity as opposed to speed, the scalar equivalent. So velocity would be something like I'm going 10 miles per hour in the direction east or something like that. Whereas speed would be like I'm going 10 miles per hour. So if we say velocity, we're really technically talking about a vector quantity, something with both magnitude and direction. Something like acceleration is another example where I'm accelerating a certain magnitude in a certain direction. So for instance, if I'm driving down the road and I hit the brakes in my car, am I decelerating? Well, no, I'm kind of really accelerating in the backwards direction. Right? I'm just changing my speed, but in that direction. Something like force as a vector quantity, if I have a block like this, if I apply a force this way, that's different than if I apply a force of the same amount that direction. Right. And in fact, if I were to apply the same force at the same time, but pointing in two opposite directions, then my block just stays still, right? And this is one of the important ideas in statics is if we have something that's staying still and that's not moving, well, then the forces should all be balanced. So then we can use that constraint to work out maybe what the forces are. And, force, we might say something, I don't know, this might be a little bit imprecise. We might say something like weight might be the scalar quantity, the magnitude of the force. But if I'm applying a force in the right direction versus the left direction, those are two different forces. Those are two different vector quantities. So we have the idea of a vector having initial and terminal points. We typically draw a dot as the initial point. We draw the terminal point as an arrow, and we draw a straight line connecting them. So this is what a vector looks like. It has an initial point noted as a dot, a terminal point noted as an arrow, and a straight line connecting them. So this is always a dot and an arrow. And we might give this a name. Sometimes it's given a bold name like V in bold, but since that's obviously kind of difficult to write by hand, we often write a V with a little arrow above it, maybe sometimes like that, or I think maybe some write it like that. I typically go for the middle option, just with the kind of like almost like check mark looking arrow. We can also say what the location of the initial point is. Maybe the initial point is located at point A in some coordinate system, and the terminal point located at point B in some coordinate system. And we might say something like the vector V, we might represent it as AB with an arrow over it. Going from the initial point A to the terminal point B, note that the A is kind of closer to the like non-arrow side of the notation, and the B is closer to the arrow side of the notation. So that's kind of in line with what we would expect. Okay, so we have this idea of a vector that we have an initial point and a terminal point. This is kind of strange though, right? We're used to working with numbers. We know when two numbers are equal and so on, but what does it mean when two vectors are equal? Well, we say two vectors are equal if they have the same magnitude and direction. Very important note, they do not have to have the same initial and terminal points. So in other words, if I have this vector, that has some terminal points C and D, and maybe this is vector U, well, it looks like this one relative to vector V it looks like the same magnitude and direction. It looks like U equals V. They start and end at different points. U starts at C, V starts at A, U ends at D, V ends at B, but they're the same vector. This is a really important idea of vectors, that it's not the initial and terminal points that determine whether two vectors are the same, it's the magnitude and direction. So I can kind of pick a vector up and move it around, and it's still the same vector. It's still equal, even if I move it in space, as long as it has the same magnitude and direction. So I could say that U equals V, or that CD equals AB. This is super nice because, right, I can think of if I have a box suspended in midair, I could think of pushing on it with some force, or I could think of pulling on it with some force. And, you know, at least for our purposes here, that has the same effect on the box. So, and I mean, of course, if it's an actual box and it's hollow or something, and I'm pushing on it really hard versus pulling on it really hard, maybe that in a different model would have some different effects. But as far as just taking a rigid body and pushing it or pulling it and keeping it rigid, that has the same effect. Right. So this is super helpful for being able to move vectors around to help us with some of the other operations of vectors. You know, for instance, the vectors up here, if we had two vectors kind of two forces pushing in opposite directions, I could actually just take this force, move it over here, and see that it's got the same magnitude as the other force, but in opposite direction. And maybe I can tell something from that. I can combine my vectors together much more easily if I'm free to move them around. Okay, so what about vector addition? So how do I add two vectors together? Let's say I have, so say I have vectors U and V, and here I'm forgetting about the U and V above. We just often use U and V for vectors. So this U and V is not the same as the U's and V's up here. Sorry. So new context now, different U and V. If I have vector U, and if I have, let's say, vector V, how do I add them together? What does the vector U plus V look like? Or is it even sensible to say that that's a vector? How we define vector addition is we place the terminal point of the first vector and the initial point of the next vector together. So let's see if I can roughly make these look the same. So here's U. And then what I would do is I'll take the initial point of V, place it at the terminal point of U. And now because I've matched up, I started with two different initial points and two different terminal points, but I've matched up one terminal point with one initial point. I have something that's kind of like an overall initial point. And I have something that's like an overall terminal point. And I can draw a line between those. That line from the kind of initial point of the first vector to the terminal point of the second vector, when the like middle terminal point and initial point are matched up, that is U plus V. So I take my first vector's terminal point, overlay the second vector's initial point on that terminal point, and then I take the overall initial point to the overall terminal point. That is what I call the sum of the two vectors. What if I did this the opposite way? What if I did V plus U? I mean, at first glance, we probably wouldn't suspect that addition is necessarily commutative because we've defined it so much differently than kind of normal addition, so to speak. But here we're starting at V, we're starting at an initial point for V, and then we're taking the terminal point of V and starting the initial point of U there. And we actually notice that these actually are equal. I mean, if you forgive my not so great artistic skills. And this is called the parallelogram law. Vector addition is commutative. Vector addition is commutative because if I go kind of along the U direction first and then along the V direction, or if I went along the V direction first, then along the U direction for each of their respective magnitudes, I would get to the same endpoint, right? Like if I go 3 blocks north and then 5 blocks east, or if I went 5 blocks east and then 3 blocks north on a nice grid, I would end up at the same intersection. So vector addition is commutative by this parallelogram law. Okay, so what about what about multiplication? Well, we know that in some sense multiplication is just like repeated addition. So let's look at multiplication, but particularly what we're going to call scalar multiplication. So what if I have like a number times a vector? So what if I have number times vector? Or what if I had something like if I have V with some initial point and some terminal point, what would 2V be? 2 times V. Well, I would suspect that 2 times V this should just be V plus V, right? It should just be this vector. Or would 3 times V be? I would just tag on another V plus V plus V. In other words, 2V, maybe not write an arrow, I don't want to get that confused as a vector, but what would 2V be? Well, it would be the vector. Well, to say what a vector is, I need magnitude and direction. It would have the same direction as V, right? This initial terminal point is pointing in the same direction as V was pointing. But the magnitude has changed. It's twice as long. So I've doubled the magnitude. So 2V is a vector in the same direction as V, but double the magnitude. 3V or 4V or 10V should be the same idea, right? Same direction, 3 or 4 or 10 or whatever times the magnitude. Okay, what about negative V? So what about negative V? We might be jumping the gun a little bit here from if we wanted to be very strict about um, how we go through and create all of these new ideas, but we're going to jump forwards a little bit here and just say what negative V is going to be. So here's what V was. It was a certain magnitude in this direction. Negative V is going to be the same magnitude, but the opposite direction. In other words, I just exchange my initial and terminal points. So this is negative V. it has the same magnitude, but exactly the opposite direction. Or what's negative 2v? Well, I would just take, oops, I would just take negative v. So again, same magnitude, opposite direction. I would have negative v plus v. So to get from v originally up here to negative 2v, what did I do? Well, I went in the opposite direction and doubled the magnitude. So the opposite direction of v and double the magnitude. Okay, so what does this look like in general? What if I had a multiple of v that was like 1.5 or 3.7 or negative 2.1? What would this look like in general? So we have scalar multiplication where c is a real number. So scalar just means a real number, where vector means something that has magnitude and direction. So c v bar, c the scalar times v the vector, is the vector either it's either in the same direction as v if c is bigger than 0, or in the opposite direction of v if c is less than 0. So if I'm going to say what cv bar is, if it's a vector, I have to describe its direction. This direction is the same if c is positive or opposite if c is negative. And I have to describe its magnitude. Its magnitude is going to be the absolute value of c times the magnitude of the original vector. So we multiply the magnitude by absolute value of c. If c is positive, we keep it in the same direction. Otherwise, if c is negative, we switch directions. Okay, so what about vector subtraction then? What about the difference of two vectors? So when I say something like u minus v, what does that mean? Well, the way that I would think about this is to say that this is u plus negative v. The same thing that I would do with subtraction of real numbers. If I was going to subtract two numbers, I think of that as being the first number plus negative, or the opposite of the second number. So let's consider two vectors u and v. If I need to do u minus v or u plus negative v, let's figure out what negative v is. So negative v looks just like v, except the initial and terminal points are swapped. And if I want u plus negative v, what would I have? I'd have a copy of u, and then I have plus a copy of negative v. Let me actually change the side that my label u is on. I love OneNote for this. It makes this so much easier than doing this on a whiteboard, by the way. So u plus negative v. So now I need a copy of this. I need to put its initial point at the terminal point of u. U plus negative v gives me an initial point here, a terminal point here, and I connect the two with what should be a straight line, but apparently I can't draw a straight line. So this is u minus v. It looks a little strange, right? U minus v, like u is like this, v is like this, but u minus v kind of still goes up, but it goes to the left instead of to the right in this case. But if we think of u minus v as u plus a negative v, and we flip the direction of v and put its initial point at the end of the terminal point of u, it does make a little more sense, right? Or in other words, we know that negative v, we're swapping initial and terminal points, so we could look at the original v and just put kind of the terminal points together and go between the initial points as with respect to the original v. So that's how we get u minus v. And u minus v is, by the parallelogram law, the same as minus v plus u. So we could do that as well. Starting from this initial point here, we could go minus v and then plus u. We would get to the same terminal point, still the same as u minus v. But of course, v minus u is not the same. V minus u would look like we go along v, and then we would go along minus u. V minus u is not the same, but we do notice that v minus u, this vector here, versus u minus v, this vector here, those actually are just opposites of one another, right? Opposite of v minus u. V minus u. So u minus v and v minus u are opposites of one another. Okay, and that finishes up for today. So we have a couple more details in this section that we'll go over next time. We will continue on next time with dot product and cross product. Depending on how next time goes, we might I might post a supplement on dot and cross product, or we might just we might finish that on Wednesday, or might wrap it up on Monday. But again, you know, these last couple of class days I think are a little bit less challenging, which is kind of nice to get a little bit of a break after sequences and series. That big chapter that was also, I think, fairly challenging. So a little bit of an easy run up to the end of the course now. Just make sure that you don't forget about Unit 3 exam this week, and make sure you plan your final exam so that you're not right at that last day or two. Make sure you plan your final exam so you have some buffer in case anything goes wrong. But otherwise, I will see you all on Wednesday.